Hello everyone, today we will discuss oxidative addition and in particular Sn2 mechanism. In the last class we have finished oxidative addition concerted mechanism and we started discussing just a little bit on Sn2 mechanism. Let us get into the details of Sn2 mechanism today. Sn2 mechanism involves the nucleophilic attack on the substrate, right. In the organometallic chemistry also we do see that ligand metal complex will attack the substrate AB, where metal lone pair or negative charge will attack on the A and B. Overall you will get a Ln-Ma complex and the B minus will be sitting around. Now next step obviously will be recombination or combination of B with the metal to give rise to Ln-MaB. This is the one which we are calling the oxidative addition complex. Now the starting material Ln-M, if it is n electron species, n electron complex, the same will be true for the Ln-Ma complex, it will be all n electron complex. Finally, we will get n plus 2 electron complex. So, upon oxidative addition, total electron count will go up by 2. So, if the 16 electron species we are seeing, then upon oxidative addition the complex will have 18 electron count. Often we do see, let us say, palladium catalysis, where palladium is in, let us say, 14 or 16 electron count. After oxidative addition with aryl halide, we are going to have 18 electron count for the oxidative addition complex. The famous substrate which usually people discuss for oxidative addition is methyl iodide. Of course, methyl iodide you can have nucleophilic attack on the CH3 group and the iodide can go out. You cannot do such thing with, let us say, tertiary butyl fluoride, the Sn2 reaction will not be feasible. Now if we would like to discuss one of the complex, we will be discussing two such cases. One of the complex, let us say tungsten complex, tungsten pentacarbonyl dianionic species, it is having 18 electron count. All of you are familiar by now about the electron count. So this is the 18 electron species. Tungsten is in +2 oxidation state. Tungsten electronic configuration is D4, tungsten is D4S2 electronic configuration. Now the total electron count becomes 18 electron. If you are adding HX to this tungsten pentacarbonyl dianionic species, overall we will have H protonation of this, basically HWCO5 minus. Now you will have X minus going out of this, right. Now in this case we are still having 18 electron complex, as we were trying to discuss. While the nucleophilic attack is happening, both the starting material and the species generated upon nucleophilic attack will have the same electron count. Then the recombination of the anion will give rise to the increase of electron count by +2. In this case, since it is already 18 electron count, we will not see the recombination or the combination of X minus with tungsten. This process will not be feasible. So we will have overall the final species as this one as the final species, right. So the final species one may expect as this one, but this one is not going to happen because it is going to be 20 electron complex. So tungsten tetracarbonyl species, dianionic species, upon oxidative addition of HX, we will overall see a protonation of the pentacarbonyl species to give HWCO5 minus, the X minus will not combine with the tungsten. So, therefore, we will not get the 20 electron complex, finally, we will get the 18 electron complex. Now, we will try to discuss another complex for its oxidative addition. The famous complex is the Vasquez complex, right. It is a iridium complex. We have discussed, I guess, previously also. The Vasquez complex is the iridium complex. It is a trans geometry for, let us say, PPH3 if you are drawing, or you can write as PR3 with the chloro and the carbonyl species. This is called as Vasquez complex. Okay. Now, if you do the electron count for this species, you will find that it is a 16 electron species. Okay. Now, if we are having methyl iodide addition with it, the species that we are going to get is iridium methyl iodide addition complex. Now, this species overall will have again 18 electron count for this species. Now, the Vasquez complex, which is a 16 electron species, reacting with methyl iodide to give the 18 electron species. Now, few things are to be noted. First of all, this is, you can see the trans addition type of thing, where methyl is on the trans side of the iodide, right. But usually for concerted mechanism, we have previously seen, for concerted mechanism, we can have first the cis addition, but for Sn2 reaction, as you know, backside attack is favorable, we will usually get a trans addition complex. In this case, the Vasquez complex, which is a 16 electron complex, undergoing oxidative addition with methyl iodide to give the 18 electron complex, where methyl and iodide are trans to each other. If we try to analyze this reaction a little bit in detail, we will see, of course, the first form intermediate will be the one where methyl is attached with the iridium complex, iodide is a anion, counter anion rather, and we have overall a 5 coordinated complex as an intermediate. This complex will then bind with the iridium, that iodide will then bind with the iridium to give the final 18 electron complex. Now, the first step, which is the attack of methyl iodide, this is the one which is the slow step, and this is where it is the Sn2 reaction. The second step, where iodide is combining with the metal center, this is the one that is going to be the first one. So, traditional Sn2 type of reaction mechanism will follow, and if you follow the reaction kinetics for this reaction, you will get a reproducible kinetics. For this reaction of Vasquez complex with methyl iodide, we will get reproducible kinetics data. That invariably means that we are not having a radical mechanism, right. So, the experimental observation for these reactions include, first of all, as I told, it is reproducible kinetics. Reproducible kinetics means if you keep on doing the kinetic studies, the data will be reliable and it will not differ too much. The rate law for these reactions will be essentially d product formation by dt, dp dt will be rate constant times iridium complex and methyl iodide complex. So, it will be first order with respect to iridium and first order with respect to the methyl iodide. This confirms that this is not a radical mechanism. That is essential to understand, that it is not a radical mechanism, and the rate law will follow first order with respect to the iridium complex and first order with respect to methyl iodide. essentially, since it is not a radical mechanism, the other way to prove this is to add various radical traps for this reaction. There are plenty of radical traps available depending on the reaction condition. We can discuss about the different radical traps, but essentially no matter what radical trap you use, you will see that the reaction is not getting stopped. So, radical trap will not have any effect on the reaction rate, again verifying that it is not a radical mechanism for this reaction. So, no effect of radical trap. Now, as you have seen, the reaction intermediate involves the attack of methyl iodide or attack on methyl iodide to give a cationic and anionic species. Therefore, if you take a polar solvent, you will see a lot of solvent effect. If you change the solvent from polar to non-polar, the reaction rate variation you will be able to say. Right. So, polar solvent will end up affect the reaction condition. As you see, for the concerted reaction, the solvent will not have much effect overall in the reaction rate, but in this case we will see that the polar solvent will have strong effect on the reaction outcome, or so to speak the rate of the reaction. So, polar solvent we can add as an observation. Polar solvent we can have a lot of reaction effect by polar solvent. More polar solvent, that means we will have further faster rate. More polar solvent will have faster rate. Of course, another feature of this reaction will be that the intermediate species, where methyl iodide is getting attacked, that species is going to be the one where we can see that it is a kinetically favored product. Once again, it is confirming that it is not a radical mechanism and not definitely a concerted mechanism. If it was a concerted mechanism, that the first form intermediate will not be seen, thereby this Sn2 reaction, this observation can rule out the formation of a concerted mechanism or radical step. So, once again, just to repeat, what we usually expect for Sn2 reaction is it is a first order with respect to both the component, that means the organometallic species and the methyl iodide in this case, and the first form intermediate is the one which is the kinetically favored pathway or kinetically favored intermediate, that involves the slowest step. The first step is going to be the slowest step, second step is going to be the faster one, and therefore, we will see overall the oxidative addition of methyl iodide from 16 electron complex to 18 electron complex. The kinetics is completely reproducible, that tells us that it is not a radical mechanism. If we add various radical traps for this reaction, we will not see any effect. Since the reaction involves a polar intermediate, we can expect the polar solvent, various polar solvent like DMF, DMSO we can take, and polar solvent will have great effect on this reaction. More polar the solvent will get a faster rate. Of course, then as the research progresses, we have to design the reaction to probe the nature of these reactions. Thereby, in the Vasquez complex, if we are not having triphenyl phosphine, if we take simple PR3 and then the R group of the PR3 is varied, we can then perhaps get more idea about the reaction, specifically the mechanism of the reaction. Let us see, take one systematic example of such PR3 groups on the Vasquez complex, and see how the reaction varies or how the relative rate varies when R is varying. We will draw the Vasquez complex again, that is again your iridium complex. In this case we are not defining the R, it is Pr3, this is CO chloride, again 16 electron complex, this is Vasquez complex. If we have ligand, so this Pr3 ligand, various ligand such as PME3, PME2PH, PMEPH2, and if we measure the relative rate, okay, in this case what we can expect, and this is what usually researcher looks at as a problem to solve, or to get more idea we can probe different R and try to gather information about the reaction. Now, since it is a nucleophilic attack, you would agree with me that if we increase the electron density on the metal center without crowding the metal center too much, then the nucleophilic attack on the methyl iodide will be expedited, will be faster, right. Now, these three different ligands we have taken, one is trimethylphosphine, one is dimethylphenylphosphine, another is methyl diphenylphosphine. If you just measure the relative reaction rate, no need to go for the absolute one, we will see that the relative reaction rate will be the fastest when we have trimethylphosphine, because trimethylphosphine is the smallest one and the most electron rich one. Therefore, electron density on the trimethylphosphine will be the maximum out of these three ligands, and also trimethylphosphine is least bulky. So, the nucleophilic attack will be preferred by the iridium complex in case of trimethylphosphine, and the kinetic study will show that the PME3 kinetics data is the maximum. If you just want to put the value, for example, we are discussing about PME3, PME2PH and PMEPH. If you set the last one as 1, we will get this is the highest 14, and these are again relative value. So, from top to bottom we will get that it is high value to low value. This value once again can be explained by the size of the ligand and also by the electron richness of the ligand. In this case, trimethylphosphine is the smallest in size and also most electron rich, and therefore, the relative rate constant is the highest in case of trimethylphosphine. Okay. Now, in terms of oxidative addition, sometimes what we see is the oxidative addition can be made faster by adding a number of additives. If you look at the research papers, often we do see that the researchers are using a number of additives. Sometimes from distance we may not be able to judge the proper reason behind adding a particular additive. Sometimes you say molecular sieves, sometimes you see, let us say in these cases they will add potassium iodide or any other iodide source. When oxidative addition is going on with, let us say, methyl iodide, they will add potassium iodide as an additive. But are the researchers just adding this for fun, or there is a scientific ground, scientific explanation or observation behind this? So, this is what we are going to discuss next, and that is what is called anion accelerated oxidative addition. It is a part of oxidative addition. It is called anion accelerated oxidative addition. Now, if you take the rhodium complex, diiodo complex, diiodo dicarbonyl complex, you want to do the addition with methyl iodide, you will get a very slow reaction to get the oxidative addition RHI3 CO2 methyl minus, right. Now, the starting complex rhodium is 1 plus, as you know, the final complex it will have 3 plus. Now, the first complex is 16 electron complex. Of course, the first complex starting complex is 16 electron complex, and the final complex is going to be the 18 electron complex. Now, this is a slow reaction, indeed a very slow reaction. How can you make it fast? If you look at the literature, if you look at the research papers, what they have done is very simply added some iodide source with it. If you add the iodide source, immediately what we will get is the fast form intermediate, that is rhodium I3 CO2 2 minus. Now, this is what is going to be the 18 electron complex. Now, essentially what we are trying to do is, in addition to methyl iodide, we are adding, let us say, potassium iodide with it or sodium iodide with it. Any iodide salt can be added with methyl iodide, and in this particular case a slow reaction can be accelerated. If we add an iodide source, iodide salt, we will get first a I3 2 minus complex, rhodium I3 dicarbonyl 2 minus complex. Now, that species is going to be much more nucleophilic compared to the starting 1 minus species. With that species, if we now have methyl iodide, since we have methyl iodide and is iodide salt together, after formation of the 2 minus species, that RHI3 species will then attack on methyl iodide quite faster. This species will add to methyl iodide quite faster to give the product formation. So, overall if we see, simply methyl iodide will give a slower reaction. By addition of iodide I minus, we will get a very fast reaction. This is what is usually known as anion accelerated oxidative addition. We do not need to add the iodide salt in large quantity. A catalytic amount of iodide salt will be good enough, because we are having catalytic amount of iodide salt and methyl iodide, let us say in stoichiometric amount. Therefore, the iodide that is coming out from methyl iodide will be acting as a next catalyst. Okay. That is why initiation of the reaction is important with an salt, iodide salt, but once the reaction is initiated, methyl iodide from methyl iodide will take care of the reaction, and the reaction will be going very fast. So, what we have learned today is Sn2 mechanism of oxidative addition. We have seen the protonation first, and then we have seen the Vasquez complex, where the iridium complex we have discussed is undergoing oxidative addition with methyl iodide to give the species or the final product in the trans geometry. Methyl is trans to the iodide, and we have seen the characteristic of an Sn2 reaction, which is distinct from radical mechanism and the concerted mechanism. We have subsequently discussed the oxidative addition, one example where the reaction itself is not fast enough, it is rather very sluggish. Methyl iodide in addition, if we have some other iodide salt such as potassium iodide or sodium iodide, pinch of it, catalytic amount, we can make that reaction faster, because it forms an intermediate species which is more nucleophilic in nature by virtue of having more charge density or more charge on the organometallic intermediate. Now, this is the species which is the doubly charged intermediate or more negatively charged intermediate will then undergo Sn2 reaction on methyl iodide. This is what is known as anion accelerated oxidative addition. So, today we will conclude over here the oxidative addition of Sn2 reaction. In the next class, we will discuss oxidative addition by radical mechanism. Thank you, keep studying, and of course, please study from standard textbook as we have mentioned at the beginning of the class. Okay, bye bye.